Hello. Hello. Okay. Thank you for being here, everyone. So I want to thank you for joining us for this evening for this book talk. I'm Greg Keston. I teach in the physics department and serve as the associate director of science ed. So on behalf of us at the Harvard Division of Science, the Harvard Bookstore, and Harvard Libraries, I'm very excited to welcome you to this Harvard Science Book Talk with Professor Jim Al-Khalili, which we're very excited to hear about his book, The Joy of Science. I have my copy right here, and I very much enjoyed reading it. But before we get into that and my introduction of our wonderful speaker, I just want to just introduce a couple things about our series here. So our series is the Harvard Science Book Talks, and we have a website. You can just Google Harvard Science Book Talks. We also have a bunch of videos of our past book talks, cosmology, geology, genetics. So if you just look on YouTube, Harvard Science Book Talks, you'll find a lot of those there. And our upcoming talks, we have, for example, Kip Thorne, who's going to talk about the warped side of our universe, black holes, wormholes, things like that. We have a talk on exoplanets. So you can find our website, Harvard Science Book Talks. But tonight, I'm very excited to introduce Professor Jim Al-Khalili, who I've been watching on the BBC for many years. So it's a great honor to introduce him. And he joins us all the way from University of Surrey, where he is professor of theoretical physics and chair in the public engagement of science. And he's written 14 books, including The World According to Physics, Paradox, Quantum, A Guide for the Perplexed, which is great if you haven't studied quantum, but even more so if you have. He's a regular presenter on many science documentaries, BBC and beyond, and he hosts a long-running weekly BBC Radio 4 program, The Life Scientific. And just in the interest of not keeping you here all night, I'm not going to list all of his numerous scientific communication awards and other awards. We were talking before, and I was asking, how many honorary PhDs do you have? And he couldn't remember. He said 8 or 9 honorary PhDs. He's a fellow of the Royal Society, and I could go on. Publishers Weekly went on about the book and said what it does is it empowers readers to critically think and evaluate the news as well as our own knowledge and beliefs. And readers overwhelmed by information overload will find the book a balm, like a calming balm, which I think in these days of information overload is very welcomed. And I just want to say, in reading it, I very much enjoyed it, its embrace of uncertainty. There are also there's a list of facts. For example, if you just look, it says humans have walked on the moon, and it just says true. And there's a list of true and false things. So it has truth in it. It has wisdom in it. It's a great guide to just use science in your daily life. And I wanted to read one quote that spoke to me, which is speaks to how approachable it is. So you say, "Nothing is beyond your understanding if you put your mind to it." So following the talk, there'll be questions. We'll come around with a microphone, so keep your questions brief and wait for the microphone to come to you. And then following that, there will be a book signing in the library across the hall with some cheese to nibble and some drinks. And you can speak to our speaker. And with that, I'll pass the podium to you, Professor Al-Khalili.
Thank you. Well, thank you very much, Greg. Good evening, everyone. Pleasure to be here. This is, in fact, the last talk of a mini book tour that I've been on for the last 2 weeks around the States. So I started off in Princeton, and then I went across up and down the West Coast, and now finally back to Boston, which is very nice because my sister lives in Beverly, and so visiting my sister and her family is a wonderful opportunity. As Greg introduced me, so half of my time is as a jobbing academic physicist. I have my grad students, I have my research program, I teach undergraduates, but I spend the other half of my time as a science communicator, and I have done for many years. And I've written, most of the popular science books that I've written have been traditional, either history of science or popular science. My previous book with the publisher's Princeton University Press, called The World According to Physics. But this book that I want to talk about this evening is a bit of a departure, because I'm partly writing stuff that there are philosophers of science and sociologists and psychologists and people who work in education policy who probably know a lot more and who've thought about some of the problems we face that I deal with in the book a lot more than me. And here I am, sort of a quantum physicist barging in, expressing my views on the matter. But I think it's important. It's an important message, particularly in the times we live in today, where we are bombarded with information all the time, and the average person, doesn't have the time to dig in and find out, what the truth is, who to trust, what the evidence is. But also, we live in a time with, as we know from the news, of polarized opinions, where everything's black and white. Everything is you're with me or you're against me. So the message in this book is partly from the title, The Joy of Science, which, by the way, when my publisher, my editor, was suggesting titles, she said, something like, The Joy of, because it reminds me of another book that's very popular, The Joy of Cooking. So to who? There's some, it's a chef from the 1960s, I forget her name now, but famous book, The Joy of Cooking. I said, you do know there's another book, actually The Joy of, and it begins with an S, that most people are going to associate with. Oh, I didn't think of that. Wow. That's Anyway, so The Joy of Science is partly to get across my passion for science and why I think it's wonderful and why it enriches our lives, but also why it's important. Why it's important to have a more scientifically literate society, and what are the lessons we can learn from the way we do science if it's done properly and honestly. I suspect I'm talking here at Harvard to an audience who sort of may well be predominantly scientifically trained anyway, so I may well be preaching to the converted, but getting a few ground sort of definitions down I think is useful. So first of all, the fact that science is not a collection of facts about the world. Let's move that cursor out of the way. There we go. Science is not a collection of facts about the world. That's called knowledge. And there are lots of ways of gaining knowledge about our world, not just through science, but through art and literature and culture and history and talking to people who know more about a subject than you, reading books, contemplation. But science happens to be a particularly reliable way of learning about our world, how it works, our place in the universe, and so on. It's a way of getting knowledge, and therefore it's a process. Science is not a collection of facts, the bones in the body, the periodic table of elements, the planets in the solar system. Those are facts. Maybe that's knowledge that we have gained from a scientific understanding of the world, but science itself is a process, a way of thinking to make sense of the world. And it relies on what we call the scientific method. In fact, scientific methods, because there's more than one way of doing science, and that is reflected by the fact that science is very wide, very broad. One of the things I do, something that takes up a large chunk of my time as a science communicator, is that I present a now long-running series on BBC Radio in the UK, the Life Scientific. It's been going for 12 years. Once it gets transmitted on radio, it then goes on to podcasts, and so hopefully people in the US will also get to hear it. And over the 12 years, I've interviewed coming up to 300 guests. The last one I recorded was when I was with Princeton, which was with Edward Witten, the father of string theory and M theory. So that was a fun thing to do. So it's the scientists who've changed our world, but I talk to them about their lives and their passions and what drives them. And I've just come to realize that science is just so broad. You could imagine the sorts of people who do science do it they require different skills The idea that, you have to be good at math to do science. Well, not all science requires that level of mathematical expertise. So the question is, why then is it important to spread the word, to explain how and why we do science? Why should society be thinking more scientifically? And I'll list 3 reasons. One I'll list, another one I'll go into in more depth, and I'll finally end with a third one. First of all, being more scientifically literate is empowering. It benefits us. When we make decisions in our complex daily lives, having a scientific understanding helps us make decisions. Anything from whether or not to wear face masks, whether you should floss, whether you should recycle your garbage, what do you do about climate change? Understanding a bit more of why you should make certain decisions is empowering and absolutely important, particularly in democratic societies where you can then elect the people who would enact those policies that reflect a better scientific understanding of the world. Secondly, the scientific method itself, and that's essentially the subject matter of this book. What I argue is the way we do science, some of the lessons that we are trained, that in ways to behave, ways to carry out our scientific endeavor, can be exported into everyday life. There are a number of things. I'll go through them. So, what is the scientific method? Well, it depends what sort of science you do. You can imagine the astronomer, the cosmologist, gazing up at the heavens, trying to understand our place in the universe. The clinician who carries out clinical trials to work out the efficacy of a drug or a vaccine. The chemist who's trying to understand the structure of matter. The climate modeler who's writing computer codes to try and predict how the Earth's climate will behave. And then, the Einsteins who are writing algebra on blackboards. They're all doing science, right? But it's very different, and it requires different skills, different talents. So what is this thing called the scientific method? Well, one way of defining, what is science? One way of defining science is about being curious about the world. So very often we talk about the fact that all children are natural-born scientists because all children are curious. They just don't stop asking the why question. But most children grow up to be adults who stop asking why because they're getting on with their lives. Then they have daily concerns, which means they're not, constantly curious about finding answers. Very often it's said that scientists are those children who've never grown up because scientists never stop asking the why questions. Being curious, then, is that enough? Well, no, I don't think so. Lots of people are curious. It doesn't mean you're curious in the right way. Very often we talk about science as being about coming up with a hypothesis, making a prediction, then looking for evidence or data to support that narrative, that hypothesis. But of course, historians do that as well. Right? A historian comes up with a narrative to describe something happened in history, and then they look for evidence to support that, or they find the evidence and try and interpret it. Is history then a part of science? No. But history and science use this same approach of testing, wanting evidence to support your hypothesis. Is science, we talk about a scientific theory as making a prediction about the world, and then if you test it, the scientific theory, that lives to fight another day. It doesn't mean it's the truth. It just means it's our current best theory that fits the observations and the data. But a conspiracy theorist would argue that they are doing science. They're coming up with a hypothesis. They are trying to understand the world, understand the evidence. They're trying to interpret that evidence. But there's a difference, a very important difference between a conspiracy theorist and a scientist in the way they think. Ask a conspiracy theorist, what evidence, what data could I present to you that would persuade you you are wrong? And they would have to say, well, they wouldn't admit it, but nothing would, right? By definition, a conspiracy theorist is not going to change their minds. You present them with data. To the contrary, they will dismiss it as fake news. The flimsiest of data to support their argument, they'll hold it up as evidence that they are right. They will suffer from what's called cognitive dissonance. according to psychologists. A sense of discomfort when faced with something that doesn't fit with your narrative, with your worldview, and so you dismiss it. Whereas a scientist, a good scientist, and not all scientists are good scientists, but if science is done properly, by definition, faced with new evidence, we have to update our worldview. What about this idea that science, a scientific theory, is one that makes a prediction that we can test? And if it tests and it comes out to be true, then that theory is held in higher regard. Well, astrologers make predictions. You know, what if your star chart tells you that next Tuesday you'll get good news, and sure enough, you're going to work next Tuesday and you get promotion. There you go. Your astrological prediction came true. Does that mean astrology is a science? No. Astrology is a load of rubbish. It's utter nonsense, right? There's nothing in it at all. But it made a prediction that came true. There's an opposite argument. Those of you physicists in the audience, you might remember some years back, there was an experiment where the particle accelerator at CERN had produced a beam of subatomic particles, neutrinos, and it fired them through the Earth. Neutrinos interact very weakly with normal matter, so as far as they're concerned, the ground, solid ground, is transparent. Travel through the ground in a straight line, and they're captured in a laboratory under a mountain in Italy. So they travel that distance from Switzerland, from Geneva to this mountain in northern Italy. And they're captured with detectors, and the scientists were measuring how fast they were traveling. They know exactly the distance, and they could, with their timing devices, they could work out their speed. And they calculated they were traveling faster than the speed of light. So, cue, press conference and excitement, and exciting. We proved Einstein wrong. We have found particles that travel faster than light. Well, I and most physicists who've studied relativity theory were, you might guess, skeptical. And we said, no, you must have done something wrong. In fact, I very foolishly went beyond that, and so on Twitter, I said, if these neutrinos really are traveling faster than light and proven to be correct, I will eat my boxer shorts live on TV. Forgetting that journalists follow me on Twitter, and before I knew it, I was being interviewed by a news program, Newsnight, on the BBC. And people were emailing me recipes for sauces to add to barbecued boxer shorts. My wife wasn't too happy. She said, look, don't make silly statements like that again. But why? I mean, here we have an astrological prediction that came true because you got the promotion that it predicted. And here we have a scientific theory, Einstein's theory of relativity, that says particles, nothing can travel faster than light, and it was proven to be wrong. Why was scientists so intransigent? Well, the point is, relativity theory has been proven to be correct, and the speed of light, that speed that light can travel in a vacuum, has been shown time and time again to be a barrier in our universe. It's part of the structure of space-time. There's no such thing as faster than light. Maybe we're wrong. Are we being that arrogant? Well, in fact, the coda to the story is that a few days after the announcement of the result of this experiment, the scientists at the Gran Sasso laboratory, the laboratory underground in Italy, realized that one of the cables behind the timing devices hadn't been clicked in properly. And so they gave it a twist, clicked into place, and sure enough, the speed dropped down just below the speed of light, as theory would predict. So my boxer shorts were safe, and relativity was safe. And the thing is, science, the theories that we trust in science are those that have made predictions and that have been shown to fit observations and data time and time again, building our confidence that they're right. Whereas an astrological prediction is a pure guess. No one mentions all those people whose birthdays, who share that star sign, didn't get any good news next Tuesday. They're forgotten about. The ones that do get some good news hold up that as evidence that that's correct. So making predictions isn't enough. Now, of course, very often, science is held up with too high a regard and used to promote all sorts of ideas that are not scientific. The sort of, I guess, the modern example of snake oil is the commercials on TV, the advertising a new kind of face cream that makes you look 10, 15, 20 years younger, or a new prebiotic yogurt that is great for your gut. Or all you have to have is an actor in a white lab coat quoting some chemical terminology, and that's science, right? That must be true. That must be good for me. I'll buy it. Not all science is good science. And also people use science, as we've seen in the pandemic. People will use what they argue is good science to argue an ideological viewpoint, not to argue facts. And they will use what they would regard as good evidence. So it's not surprising that so many people in wider society don't know who to trust, don't know who to believe. The example I often use is during the pandemic when it first hit. The advice, public health advice, was wash your hands. Wash your hands thoroughly while singing happy birthday two times over, because that's enough time then to make sure your hands were clean. And then by the summer of 2020, it became clear that COVID was airborne, and therefore the advice was wear masks, social distance, open windows. And a lot of people said, well, hang on a minute, you told us that we had to wash our hands and that will be enough not to catch COVID. Now you're telling us to wear masks and open windows. Stop changing your mind. You know nothing. And they lost their trust in science because they didn't understand how science works. That we do update our theories in the light of new evidence and data. So I'm going to go through a few lessons of the scientific method, the way we should do science if it's done properly, and whether they have a bearing on and usefulness in everyday life. The first one is a bit controversial, because I say something is either true or it isn't. I see Veritas as the Harvard symbol here, right? Is there such a thing as truth? Well, for me, in my area of physics, yes, the universe behaves in a certain way. We should never be absolutely certain that if I jump off a roof, I'll fall downwards. It may be that, there's an unwritten law of physics that said on a particular morning, at a particular time, gravity suddenly becomes repulsive and I float upwards. But there is a truth, there is a way, an objective reality, a universe out there regardless of our own subjective views. In wider society, in everyday life, of course, it's far cloudier, far hazier. Whose truth? But it's dangerous to push that too far. In the notion of cultural relativism, in its pure sense, it's a good thing. It's essentially acknowledging, respecting other cultures. A cultural worldview from one perspective doesn't necessarily mean that is the truth. There are others who have a different worldview, a different viewpoint, who might disagree. So who is right? But cultural relativism doesn't mean that all truths are relative. That my truth is as well, Donald Trump said that, didn't he? Was it something about this alternative facts? But when it comes to things like ethics and moral arguments, it's not so clear-cut. Here's 4 moral truths. Showing kindness and compassion is a good thing. Murder is wrong. Human suffering is bad. Actions more likely to bring harm than benefit are bad. So on the face of it, reading this, you think, yep, okay, well, I can't really argue with those. But you can always find counterexamples. Showing kindness and compassion is a good thing. Well, that's sort of a tautology. It doesn't say anything. You might as well say being good is good. Right? There's nothing in it. Murder is wrong. Well, okay, we can all think of examples where, the classic one in sort of Ethics 101 is, if you went back in time and you could take out Adolf Hitler before the Holocaust, would you do it? Right? You'll murder him. But is that wrong if you're saving millions of lives? Human suffering is bad. Well, not all human suffering is bad. Guilt, grief, they're forms of suffering. Grief isn't bad. It's what defines the human spirit. So again, not all suffering is bad. And then actions more likely to bring harm than benefit are bad. Well, it depends who for. Some actions might bring benefit for some, but harm for others. And then what do? You have to weigh, what overall, whether it's a good thing to do or not. So moral truths, it could be argued there is no such thing as an absolute moral truth. But in science, Greg mentioned one example of what I call facts. with the proviso, as I'll mention in a moment, we should never be 100% certain. But some ideas about how the world is, we are so confident about that we might as well call them facts. So I'll list a few, including the one that was mentioned in the introduction. Humans have walked on the moon. True. The Earth is flat. Not true. Life on Earth evolved through a process of natural selection. True. The world was created about 6,000 years ago. Not true. Earth's climate is changing, mainly due to humanity's actions. Increasingly, we're seeing. That's undeniably true. Nothing travels through space faster than light in a vacuum. Yeah, despite that experiment, turned out that was wrong. True. Give or take, there are roughly 7 billion atoms in the human body. Now, I haven't counted them myself, but that's sort of a good order of magnitude. That's true. And finally, I don't know if this made it here to the US, but at the UK, there was a movement saying that 5G masks were contributing to the spread of viruses. The alternative was that, well, it was all down to Bill Gates trying to implant chips for mind control. Not true. Now, I call these facts, and sort of particularly the ones that rely on our understanding of the physical universe. The point is that were the opposite to what I've put up there the correct answer, we would have to dismantle and rebuild the whole edifice of modern science. A theory that you come up with, if you say world was created 6,000 years ago, or that something can travel faster than light, or the Earth is flat, then the onus on you is for that explanation, that theory, to match and fit all other observational data and evidence that we've accumulated over the last few centuries. And we would have to take out the whole of modern science and rebuild it. And weirdly, the people who believe in sort of strange ideas like that tend to be using the very technology, their laptops and smartphones, that utilize the science that they're disagreeing with. But I call these facts not because I'm trying to stress that I'm 100% certain. It could be that you should never be 100% certain about anything. It could be that the moon landings were all a conspiracy. I just very, 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 very highly doubt it. But there is an objective reality out there. There is a truth out there. And it's not just down to our viewpoint or, I've just decided I don't want to believe your version of something about the world. I want to believe what I want to believe. And in science, we can't do that. And very often in everyday life, we shouldn't be doing that. But everyday life is messier. And it's harder to disentangle what is true from what isn't based on who you're listening to, what the evidence is, what's the source of that information and evidence, and so on. Not everything is as simple as you think. We've learned that the hard way in science, that we might want a simple narrative, a simple explanation of the world, but increasingly we realize that dig deeper, you find something richer, a richer reality, or a more complex explanation of things. We want something to be simple, but very often it isn't. And that's even more true in everyday life. And we know, for example, from the news that we're watching and listening to at the moment, just how complex some issues can be. We know what the sort of, the transgender rights versus feminism, for example. There's always it seems increasingly a black and a white. In science, there isn't black and white. In science, there's gray, there's nuance, there's complexity. Issues that are complex require debate. Scientists are used to making slow progress because they're trying to understand a complicated or complex phenomenon that needs lots of evidence, that needs careful experimental data that is reproduced, that's replicated before we can make any statements. But we're very quick to jump to deciding, based on our ideological view, where we stand on a very complex issue, a societal issue. Not everything is black and white. And we see this amplified by the internet and by social media, that those on the extremes are the ones that shout the loudest. The middle of the bell curve, where the majority of people tend to be, shy away from even engaging in debate and discussion, because we know that very often, because of the black and white polarization, you're not allowed to say, well, you've got a point, but you have also got a point. No, both sides will then attack you. You have to take sides. You can't sit on the fence. We don't behave that way in science. We try not to. There will be scientists who've built their whole reputation on a particular theory or experimental result, and that's, whether it gets them promotion or tenure or the respect of their peers or a bonus for whatever technology company they work for. They don't want to be told that they're wrong, that there's another point of view. But the scientific method, in principle, should be self-correcting. The consensus view is there for a reason. Just because you don't understand something doesn't mean you can't if you try. Okay? I don't mean that we can all become experts in quantum theory if we just put in a bit of effort, people. We can all do it. There are certain things that require expertise, and they're experts because they have a talent, or that they've spent years training or studying. That's why they know more about something than you do. I don't tell my plumber, don't worry about fixing my boiler or my plumbing. I've had a look at a 3-minute video and I know what to do. No, my plumber knows that's his job. He's trained to have that expertise. In the same way that I don't insist that I'm as good as a concert pianist or a 100-meter runner. Or you don't tell your dentist, don't worry, I'll do my own fillings, thank you very much. You don't tell the pilot, don't worry, I can fly this plane. These are people who've spent time learning something. But my point is that doesn't absolve us from any responsibility to try and learn a little more if we put in some effort, rather than dismiss subjects or topics or issues because they're too complicated or because they don't fit the narrative and don't fit into our sort of bubble, our ideological bubble. Doesn't really work. We should be putting more effort into trying to dig a little deeper. Don't value opinion over evidence. We hear that a lot, and we hear that a lot, certainly, in arguments on social media. Two views are not necessarily equally valid. If one of them relies on evidence, data, reliable sources, and the other is just because you've listened to someone who you happen to agree with, that doesn't make it right. Opinion over evidence doesn't work in science. You may want a theory to be right, that doesn't make it so. You may want your experimental result to make a prediction about how the world works, that doesn't mean you're right. You'll be found out in the end, because science progresses through consensus and repeatability and so on. Right. Recognize your own biases before judging those of others. That's something we have to do in science. If I'm working on a particular area of research and I've got some result that I want to write up in a paper that I'm going to submit to a peer-reviewed journal, I better check my results first. Your experimental results or your calculation, your computer code has spewed out some numbers. You check and check and check to make sure that what you've done is right. Because if you make a mistake, you'll be found out in the end. So better you check and make sure that you trust your scientific findings before you tell the world about them. And that means we have to examine our biases. We're forced to say, just because I want this particular scientific result doesn't make it so, doesn't make it true. Why do I want it? Why do I believe what I do? And I think this general idea of, in a debate or an argument with someone, don't always be quick to try and find the weaknesses in their argument. It's not all about point scoring, about winning arguments. It's about finding the truth of a matter. And it would be refreshing if people, before you attack the opposing view, take a moment to examine why you believe what you believe. Do you have some sort of bias to believing what you believe? Why do you think this way? And what's driven you to hold that opinion? Is it possible that you could be wrong? What we have to do all the time. in science. Don't be afraid to change your mind and admit your mistakes. Okay, so this is probably maybe the most important lesson. That's what we do in science. If we didn't admit our mistakes, we wouldn't progress. We would all still believe what we believed at the beginning, right? And what the ancient Greeks believed. But we learn. We change our minds. We realize that washing your hands isn't enough to stop you from catching and spreading COVID, because it's airborne. So that was a mistake. We've changed our minds. We've progressed from it. It's empowering to admit your mistakes in science. The opposite to what you see in politics, of course. In politics, it's a weakness that to admit your mistakes. For a politician to say, well, I believe in a certain economic policy, but I've just talked to economists who know a lot more about this than I do, and they've convinced me that, in fact, I was wrong, and I'm changing my mind, and I'm now pursuing a different policy. Well, that politician's dead in the water. You're not going to listen to him. But you can't just flip-flop your views. You have to be strong and stick to your guns. That doesn't work in science. I probably have time to quickly tell the story. So a few years ago, I made a documentary for the BBC about gravity. So the premise was, why does the apple fall? And so I start from Newton's law of gravitation and move on to Einstein's theory of general relativity and space-time curvature. In part of it, I talk about how time itself is affected by Einstein's theories of relativity. So I explain in the documentary that a clock placed at the North Pole, because the Earth is sort of squashed, it's oblate shaped, so it's sort of the points on the equator are further from the center than the poles. So a clock at the North Pole is closer to the center of the Earth, which means it should feel a stronger gravitational pull than a clock sitting out on the equator, which is further away. Clearly, if you take the clocks out into deep space, they're not going to feel any gravity at all. Bring them closer, 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 gravity gets stronger. So the clock at the North Pole feels a stronger gravitational field and therefore should be ticking slightly more slowly. We know this. Einstein's general theory of relativity says that time runs slower the stronger the gravitational field. Matthew McConaughey knew this very well in Interstellar, right? He's on this planet orbiting a supermassive black hole where the gravitational potential is so strong that he knows that just an hour spent on this planet and years are going to go by on Earth, and his young daughter's growing up and turning into an old lady. So time is relative, and a gravitational field changes time, the passage of time. But in this program, I say, however, if you put a clock on the equator, the Earth is spinning. And Einstein's other theory of relativity, his special theory, which he published 10 years before his general theory of gravity, in that theory, he says that objects moving very fast also time will appear to run slower for them, according to us viewing them from outside. So for someone floating out in space, the clock at the North Pole should be running slower because gravity is slowing it down, but the clock on the equator it's running slower for a different reason, because it's moving, it's special relativity. And I talk about how which clock is the one that wins, which is the one that runs slower. We'd done the program, we'd finished the filming, I was due to go in to do the voiceover, and my exec producer, Paul Sen, very smart guy, contacted me late one evening and said, I've been looking at a physics forum website. That's always a bad move. So I think we've got it wrong. He very politely said, we've got it wrong, not you've got it wrong. And because of such and such, and I don't think the clocks are, your explanation wasn't correct. I panicked. I contacted various colleagues that I know. In fact, Kip Thorne, who's coming to talk here, was one of the people I contacted. And there are young people in the audience, so I won't swear. But he basically emailed back, said, yes, Jim, you've up. It's wrong, but don't worry, we've all done it. So he's trying to sort of soften the blow. But the point was, the clocks at the North Pole and on the equator both tick at exactly the same rate, because they fall on what's called the surface of a geoid, a surface that has equal gravitational potential. All clocks at sea level, anywhere on Earth, all tick at the same rate. And I'd got it wrong. The point of this story is that we went back to the BBC and said, look, you can't transmit, we've made a mistake, we need to reshoot some stuff. And the commissioning editor said, that's fine, take a few days, shoot the bits where you're wrong, put them in the edit, no one will be any the wiser. And I said, actually, this is a really nice opportunity to show that in science, you're allowed to change your minds. What I'd really like to do is film a bit where I say, unfortunately, at this point, I realized, I said, I did the same way, producer. I wasn't going to give him the credit. I realized that I'd got something wrong in my explanation. And that, in fact, for such and such a reason. So we presented this to the commissioning editor at the BBC and said, we want to film, but we want to admit the mistake. And then, oh, no, she said, I'm worried about your reputation, Jim, as a professor of physics. You'd lose credibility if you admit your mistakes. I said, no, trust me, that's not how it works in science. And I got my way, and we reshot, and I say, unfortunately, at this point in the story, things go a bit pear-shaped, because I realized I'd got it wrong. And I then go on to explain things. And I would get people coming up to me afterwards who watched the show, and they said, oh, we're very, you're very courageous to have said that. I said, no, that's what we do in science. I'm genuinely not being, I'm not proud of the fact that I made a mistake, but I'm not proud of the fact that I was happy to admit it. That's just the way we do things in science. And I felt it was a good opportunity to explain how science works. Okay. Uncertainty and certainty is hugely important. In order to be able to admit your mistakes, you have to have been prepared for the fact that you may have been wrong. The idea of doubt is so important. Certainty, according to Voltaire, is just absurd. Yes, I said there are facts about, the Earth not being flat and that we went to the moon and so on, but when I say facts, I don't mean there's no such thing as 100% certainty. There always has to be room for doubt. And explaining the idea of uncertainty, it doesn't mean that we don't know. It means we know what we don't know. We know the extent of our confidence level in something. We know how likely it is to be right or wrong. Uncertainty is a hugely important aspect of science. And it's okay to be uncertain. What's the term in psychology? The Dunning-Kruger effect, right? Which is basically the less someone knows about a subject, the more certain they seem to be that they're right. Whereas if you're an expert on a subject, you probably know the gaps in your knowledge, and so you are more cautious. Okay, the final lesson, because I want to wrap this up, is the fact that there's an objective reality out there. So this is a picture. This is meant to be Plato's allegory of the cave. The story goes that you have these prisoners who are trapped. They're chained inside this cave, and all they get to see are shadows on the walls of the cave, made by objects, carried by people walking past, maybe chanting and singing. Let's not go into the reasons of how and why. But the point is, these prisoners think their whole reality is two-dimensional. The shadows are everything. And the sounds they hear echoing around the cave, they think are coming from the shadows themselves. And so their reality is two-dimensional. Well, if one of them happens to be set free and goes out into the real world and sees a three-dimensional world, he sees a deeper, richer reality. He realizes that shadows are simply where light is blocked from passing through solid objects. Now, if he were to go back and tell his fellow prisoners, there's this deeper reality, three-dimensional world, there's a sun, so on, they wouldn't believe him. They would think he's crazy, because that is their limited reality. Plato's point here was that the chains were the chains of ignorance, and the prisoner escaping that he is more enlightened. And, there are modern versions of it, right? There's the, Tom Hanks in The Truman Show, The Matrix, right? There's a deeper reality out there. And it may be that he's not seeing the true reality. We're not seeing the full reality. I'm not saying we're living in a simulation. That's a silly argument, and I don't entertain it. But there is a reality out there. There is a truth out there that we try and, we may never reach, but we try and get as close to it as we can. And there's no reason why we shouldn't be trying to do that in everyday life as well. Okay, so then the third and final reason why we should try to think more scientifically is simply that having a scientific understanding of the world can enrich our lives. It can add to our appreciation of the world. There's the famous Richard Feynman quote, Poets say science takes away from the beauty of stars, mere globs of gas atoms. Nothing is mere. I too see the stars on a desert night and feel them, but do I see less or more? What is the pattern or the meaning or the why? It doesn't do harm to the mystery to know a little more about it. It doesn't. Having a scientific understanding of the world doesn't turn us into cold, hard, rational Mr. Spocks. Right? It can enrich. And in the book, and that's why there's the picture of the rainbow colors. I talk about the rainbow as an example of learning more about the science. It's been other science writers have talked about it. Richard Dawkins, Carl Sagan. So this is not new ground I'm covering. But my point here is that we can all appreciate the beauty of a rainbow. It doesn't matter how many times you've seen a rainbow. Oh, look, there's a rainbow. Oh, very pretty. Having a scientific understanding can make it even more amazing. I don't mean knowing that the way the light is broken up by, bouncing, refracting through raindrops and total internal reflection and then refracting back again into your eyes. Yeah, that's optics, and it's, not so interesting. But what it does allow us to understand is that, for example, no two people see the same rainbow. Standing next to someone, what you see, so the red light that's entering your eyes has been produced by certain raindrops because they're bending the light with just the right angle for it to enter your eyes. Those raindrops are not sending red light into the eyes of the person next to you. Those are different raindrops doing it for them. And so we each see our own individual rainbow. That's a beautiful thing. Or the fact that the rainbow, the arc, never mind the pot of gold at the end, the arc is an arc because it's cut off by the ground. If you were to climb up a mountain, or if you were to be, in a plane, looking out the window, if you're lucky enough, you could see a rainbow in its full glory as a complete circle. And it's just it's a circular object, but it's cut off by the ground because of our perspective. It's a cone of light that enters your eyes. So those things, that the rainbow is a full circle, that we each see our individual rainbows, I think adds to the wonder, adds to the beauty of the rainbow. And there are plenty of other examples. I was over on the West Coast last weekend, and they had a annular eclipse where the moon sort of comes in front of the sun, but because the moon is slightly further away in its orbit from the Earth, it was a bit smaller, so it wasn't quite big enough to cover the full disk of the sun. So you get the ring of fire around the moon for a few minutes. I didn't have to be exactly in the path. I was up in Seattle, which so sort of 80% coverage. But again, examples like that, explaining the wonders of science and having an understanding of why we're seeing what we're seeing, adds to the awe, adds to the beauty. Doesn't detract from the mystery of science. And so that's why the book is. I'm very happy the publishers. So this is the figure 8 means 8 lessons, and I've got a couple of rainbows there. So just in case you're wondering why it's so pretty. Fine, and I think I'll leave it there and give you time to ask me some questions. So thank you very much.
Much. Wonderful, very approachable talk from somebody who does theoretical physics and has written about some of the more technical parts as well. So we'll come around with a microphone. So you can raise your hand. Please wait for us and ask your brief question. But actually, if you don't mind, I'd like to start with a question. So you briefly touch on, in the end of the book, artificial intelligence. And so I wonder if, you've thought about how these lessons can be applied when we're thinking about a world where artificial intelligence is telling us things which may or may not be true.
Artificial intelligence is an interesting problem. Most of what I talk about AI in the context of the book is that we know that AI is getting increasingly sophisticated at deceiving us. Where not just images, but even sort of video. And how do you then know what is true and what isn't? AI is a technology that's coming at us very fast. We know we haven't even had ChatGPT for a year yet, and yet how much it's changed our thinking in so many in our working lives. So we can't slow it down. but we can make sure we're ready for it. We certainly have to make sure we're ready for it in terms of, the ethical implications and putting regulations in place. But I argue in the book we can also use AI to help us. The good AI versus the bad AI, right? We already use, some form of, filtering of spam emails as something that's been happening for years. So we don't get the emails from the Nigerian princes wanting to invest, or other weird and wacky emails. And I think AI can be used to help us tackle the AI that's trying to deceive us. It's going to be increasingly, it's already difficult to know who to believe and who to trust, right? What we read, what we see online. And if AI is going to just make that problem harder, then we're going to, whether we like it or not, need the help of AI to battle against it. So I think, AI is not always a force of evil. We can also use it as a force of good.
Great, thank you. Oh, right here.
Thanks for sharing. I'm studying history, and one of my professors made the exact same argument with you a few days ago, but he's suggesting how to think more historically to benefit decision-making. So I'm wondering, could you share a few more words on how do you see the relationship between history and science?
I mean, the similarities that they have, I think, is, history is one of those subjects where, like many scientists, I probably didn't like when I was a kid at school. And then you reach adulthood and you realize just how wonderful a subject it is, and you realize you want to be catching up. It shares with science the notion that you're seeking the truth. I mean, very often in history, things can be a bit more shady. Whose truth, from which perspective, the victor or those who's lost their civilizations. I mean, stories are told in different ways, and history very often is about stories. Science is also about stories and narratives, but they are what we want is to use them to interpret, say, mathematical theories to tell us the truth of how reality is, and reality is only one way. The best example is in quantum mechanics, where you have the math, and that works, and it's very powerful, and it's helped us develop much of the modern world. But we can't agree on the narrative. We can't agree on how and why. Are there parallel universes? Are things interconnected non-locally and so on? So that's frustrating in science, that we have more than one narrative. It's less so in history, but I think they do share this wanting evidence and data to support a particular narrative. And if the data and evidence doesn't support it, you have to change that narrative. It's the same in history and science.
Hello, Jim.
Hi.
Thank you so much. That was a very nice talk.
Thank you.
I'm so excited to read the book. Maybe it's a similar question, because I really like the points that you mentioned, and being myself also a scientist, I feel that those points that you mentioned, really seeking the truth and admitting you're wrong, are qualities that should actually be beyond only scientist realm, but even our daily life, like the politicians, for example. Yeah. And I know maybe this is a side question a little bit, but how do you feel these points are critical, especially now at this very tragic time in the Middle East, where also truth and lies nowhere? What is our role as scientists in maybe transmitting? Do you feel, first of all, that these points should be transmitted to other areas? And do we have a role as scientists and so and so?
I think we do have a role as scientists in that not everyone who trains in science should stay in science. I think it's absolutely important that we have more scientifically literate politicians and policymakers and in other walks of life, in law and so on. But certainly I think one should not be arrogant enough to think that the rational scientific view is the one that can solve society's problems. What we're hearing in the news now is so raw, it's so people are so passionate about it, that a scientist coming in and saying, hey guys, let's sit down and let's think rationally about this, I don't think that's helpful. Not every issue in society can be solved with the rationality of science. I think it requires other human traits as well. that involve empathy and compassion and so on, not just seeking evidence of cold, hard facts. So yes, I think there are societal issues that the scientific method can help, but there's a time and a place for doing those. I certainly have not been involved at all on social media for the last couple of weeks because I don't think it's helpful. I don't think that adds anything or helps resolve anything or helps change hearts and minds. So one has to pick the right time to try and get society to think more rationally about the world.
Thank you for this comment and for the talk. Actually, I want to point out there is an Italian journalist turned monk, which is Tiziano Terzani. He said science is a very powerful method to acquire knowledge. The only mistake is to think that's the only one. And I think that very much resonates with what you just said.
Thank you. Yes, I mean, gaining knowledge, as I say, I don't say that because I'm trying to appeal to a wide audience and, but actually I really think science is the only way. There are aspects of human experience that are outside of what science should be telling us about. And I think it's arrogant for those scientists who feel there's a scientific answer to everything. I happen to believe it's the most reliable way of gaining an understanding of our world, of our physical universe. And we've seen that increasingly throughout history, where we believed in, whether it was superstition or whether it's religious beliefs, science has been pushing against that. And increasingly, yes, the Earth goes around the sun. Galileo was right. Human beings are not rational, no, but we have been smart enough to develop the scientific method. And the scientific method counters our base instincts, our irrationality, our motives to be right, our selfishness. The scientific method has its flaws, but I think the way we progress our understanding through the scientific process is as reliable as anything I can think of.
Good evening.
Hi.
So I'm not a scientist, so I'll preface with that. But I have a question I'm curious about in terms of scientific method and how it's applied. Throughout history, we've seen that human beings have come up with really interesting solutions for things not using scientific method. And so sometimes it seems like those make these sort of leaps and jumps much quicker, whereas oftentimes when I'm looking at articles of something that somebody's trying to prove scientifically, it's such a tiny incremental step that it almost seems like you're at risk of missing the forest for the trees, so to speak. So what are your thoughts about the role of sort of, yes, keeping to the scientific method to not just give in to opinions, but also incorporating these kinds of leaps, you could call them, of intuition, you could call them maybe just the fantastic way the human mind works and the way it connects things.
Thank you. Yeah, I mean, science is not all about incremental advances. The great advances in science very often have been the revolutions, the completely new way of thinking. We just go back to, the beginning of the 20th century, the German Max Planck, who developed quantum theory. He kicked it all off, and he's often referred to as the reluctant revolutionary, because his idea was so wacky that even he didn't believe it, and yet turned out it was right. Einstein, when we talk about Einstein as being the father of relativity theory, well, all the equations of special relativity had all been written down by people several years before Einstein comes along. Einstein's genius was that creativity, that spark of, thinking outside of the box and saying, well, maybe there is no luminiferous ether. Maybe the speed of light is constant for all observers, because if that happens, then such and such. So, yeah, I think we often need, the Newton realizing that the apple falling to the ground, whether apocryphal or not, whether it fell on his head on his mother's farm during the plague, but appreciating that the reason the apple is pulled to the ground is the same force as the one that keeps the moon in orbit around the earth and the earth in orbit around the sun. That was in no way obvious before that. Why would they be? This is the earthly forces and there's the stuff that goes on in the heavens. But to link those two and come up with the law of gravitation, that was absolutely not incremental. So I think a lot of science is incremental and has to be. We can't all go off and come up with crazy, wacky ideas every day. We need to build on the clever people that have come before us, who for good reason have their particular understanding of the world, and we advance on that. But we do also absolutely need the geniuses. I always get very annoyed when people talk about the arts and humanities as being the creative subjects versus the sciences that are not. Science is all about creativity.
I think that's a beautiful note for us to end on, but the conversation can continue in the library with the book signing and some things to nibble on. And let's give a final hand to Dr. Al-Khalili.
Thank you. Thank you very much.